all the values such that the derivative of this function evaluated at that point, in our case we're calling this value c, is equal to 0. So that is, where does it have that horizontal tangent line? Okay, so the first thing we have to do is verify whether or not we can even apply Rolle's theorem. So we have to check for two things. The first is continuity. And the second we check for is f differentiable. Well, first of all, f is a polynomial. As such, it is both continuous and differentiable. So actually, here's what I'm going to do. It is both continuous and differentiable. So for all real numbers, so what I mean, it is continuous and differentiable everywhere. This can also be looked at in this manner. All right, so the conditions of Rolle's theorem are met. We have continuity and differentiability. So now let's go ahead and find all the values, all the real numbers c, so that the derivative evaluated at that number is 0. So let's begin with f prime of x. Well, that's equal to 4x squared minus 4 plus 0. Okay, so now let's go ahead and figure out where is this derivative equal to 0. That is, where is 4x squared minus 4 equals 0? Well, that will occur wherever 4 times x squared minus 1 is equal to 0. So let's factor this difference of squares is x minus 1, x plus 1 equals 0. So there's two candidates for c, that is x equals 1 and x equals negative 1. Now let's go ahead and evaluate both of these. Okay, so let's find the derivative of our function f of x, which is equal to 2x squared minus 4x plus 5. So f prime of x is equal to 4x minus 4. Where is this equal to 0? That is, where's f prime of x equals 0? Well, that's when 4x minus 4 equals 0. Equivalently, that's x minus 1 equal to 0. So the only spot is x equals 1. So then what have we actually done? Let's just remember Rolle's theorem real quick. This spot here, when x is equal to 1, the instantaneous rate of change is 0. When x equals 1. Well, remember what Rolle's theorem tells us is this is the spot where the slope of the function is going to equal the slope between the endpoints, because the slope between negative 1 and 3 is 0. And if you want to verify this, find the average rate of change really quickly. The average on this interval is equal to f of 3 minus f of negative 1 over 3 minus negative 1. So that'll give you what? 11 minus 11 over, doesn't matter what it's going to be over, because look, this is 0. So notice the average rate of change of f on negative 1 to 3, this interval, is 0. Those of you in my class, on your own work, when you're doing these kind of assignments, you don't have to do this extra bit. It would be enough to just find this value. I just wanted to make it very, very clear that what you've done here is shown that there is a spot on this function, on this interval, such that the instantaneous rate of change is 0. And that instantaneous rate of change is equal to the average rate of change on the interval because, of course, our function evaluated at the endpoints gives us 11 each time. So the endpoints give us the same y value, meaning their average rate of change on the interval of that function has to be 0.